In this class, we're going to introduce the definite integral and a symbol for the definite integral. And we're going to discover that when it comes to rectangles, more is better. So in our last class, we estimated the area under a curve by drawing right rectangles, like in this picture. So we broke the x interval from a to b up into equal pieces. We used n equal pieces in general. In this particular picture, I broke it into 4 equal pieces. And then I built a rectangle over each of those 4 little intervals, and I determined the height of the rectangle, in this particular case, using the right-hand endpoint of the interval. So you picked the right endpoint of the interval, go up to the graph, and that's going to be the height of your rectangle. All right, so I could just as easily have used the left endpoint of the interval to get the height of the rectangle, or even the midpoint of each interval. We're just going to stick with the right endpoint today just to have some consistency. So in the last class, we saw this messy formula. We're going to talk through it again to make sure it seems reasonable. The area under the curve, which when that curve is a velocity versus time graph, represents total distance traveled. So when you're adding up you're using rectangles to estimate the area under the curve. You add them all up. Each rectangle has a width of delta t. So you've got delta t, delta t, delta t, delta t. Right? So each of those rectangles has the same width, delta t. And then the height of those rectangles is the height of the function at the right endpoint of the interval. So in this case, a would be called t sub 0. The next point would be T1, then T2, then T3, and B would have a second name, T sub 4, right? So in this case, N is 4 because I used 4 rectangles. So this first rectangle here, its width is delta T, and its height is the function value at T1, right? The right endpoint of the interval from T0 to T1 is f of T1. So this is the area of a rectangle, the first rectangle. This next term is the area of the next rectangle, and then the next rectangle, and then you just keep doing that until you get to the last rectangle. So if I wanted to write a general formula and not one where I've already picked the number of rectangles, I would write f of t sub n, meaning the very last point of my interval. It's okay. So f of tn is the height of the very last rectangle. So each of these things is just the area of a rectangle. And when you add them all up, it estimates the area under the curve. So we called this thing a Riemann sum, named after George Bernard Riemann, famous mathematician. There's actually still a very famous problem called the Riemann hypothesis that is still being attempted to solve. Oh, maybe it got solved. I don't remember. I'll look it up. No. Okay, so I can use sigma notation. If you remember from the regression project, there was a little bit of sigma notation at the end of that, which you use when you have to write a long sum. It like saves you some writing. If you have to write a long sum where every term looks kind of the same, except they only differ by maybe a subscript, like this is delta t times f of t1, delta t times f of t2, delta t times f of t3, plus blah, 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 blah. They all look exactly the same. The only thing that changes is a subscript. So if I was going to use sigma notation, I'm going to write it up here because I have more room, then I would write distance, or area under the curve, whatever, is the sum. And every term looks like delta t times f of t with some subscript, and you just name that subscript a letter. Most commonly used letters would be I, J, and K. I'll use I. And then you say, okay, you're going to add up a whole bunch of terms that all look like that. And for the i's, you're going to start with using a 1 for I, and then what's the very last I you're going to use? N. So you put an N up top. So this is the sigma notation for the right-hand Riemann sum. So what could we do if we wanted to get a better and better approximation for the area under the curve? Okay, look at the pictures. Make the intervals smaller, right? Use more rectangles, more skinnier rectangles to estimate the area. As n increases, that is the number of intervals you break A to B into. As n increases, the area of the rectangles approaches the exact area under the curve. Like this last picture, I used a lot of really tiny, skinny rectangles, and it really looks like very close to the exact area under the curve. So the more rectangles, the better. So what I'm going to do is take a limit, right? And I'm going to let n, the number of rectangles, approach infinity. That's what makes this a calculus problem. Finding the area under the curve is a calculus problem because it involves taking a limit. So full-fledged, hardcore, no messing around definition for the area under a curve. Okay. If the function is continuous on the interval a to b and positive, meaning always above the x-axis, then the area under the curve, y equals f of t over the interval from a to b, is the limit as n goes to infinity of the right-hand Riemann sum. Also the left-hand Riemann sum or the midpoint Riemann sum, but we just stick with one. We'll just pick the right-hand one to work with all the time. Does that make sense? Okay. All right, so this formula isn't something that you need to memorize, but calculating area under a curve is something we're going to do many, many times. So we're going to use some new notation to avoid having to write this whole limit thing out every time. So we're going to create some new notation. It's super important in any future calculus classes you take. We are going to let this notation denote the area under a curve over the interval from a to b. So that thing is an elongated s. So this thing stands for sum, right? And we kind of have smoothed it out, right? Because we're taking, when you take a limit, you kind of smooth out the rectangles, right? So this is a sigma, stands for sum. And the integral also stands for sum, but like a smoothed out sum, right? Where you've taken the limit. Oops. Okay. So then, the elongated s kind of encompasses all of this notation, right? It means a smoothed out sum with the limit. And then when you're taking the Riemann sum, you do the height of the rectangle times the width of the rectangle, f of ti times delta t. But when you take the limit, we just call this thing f of t, and delta t we call dt, right? The same thing when we did like derivatives, when we did, say, dy dt, right? That used to be, when we first started talking about tangent lines, we said, well, the slope of a secant line would be change in y over change in t. And then when we took a limit, that became dy dt, slope of a tangent line, right? So now instead of a delta t here, I'm using a dt when I take the limit. All right, and then we call this symbol, you would read this as the integral from a to b of some stuff dt. You usually have a function in there in the brackets. Okay, and it's called the definite integral. The numbers on the integral sign, the a and the b, are called the limits of integration. That's just the left endpoint and the right endpoint that you're finding the area between. Not to be confused with all of the limits we've been calculating this year. They just mean like the endpoints of the interval. Yes. Do you have a question? Do you have a question? Oh, okay. Okay, so the function y equals f of t, the thing you're taking the integral of, is called the integrand. All right. Yep, easy peasy. You guys do some.